Hi everyone, welcome back, and we're going to again talk about composition of functions. So the first thing, we're going to have two examples. So the first thing I want to do is talk about this example, and we're going to talk about it quite extensively. But I need to give you some terminology first. When you look at, so let's look off to the side here for a second before we do the example. When we look at f circle g of x equals f of g of x, and g circle f of x equals g of f of x, the function that's in the parentheses, so this function in this case and this function in this case, these are called the inner functions because they are inside the second set of parentheses. And then this function here in this problem, and this function here, this is known as the outer function. So I'll be using this terminology a lot in this section. So the functions that's completely contained in the second set of parentheses is the inner function, and the function that's all the way outside all the parentheses is the outer function. So let me delete that. Now that we have that terminology, we can start talking about recognizing when a function is a composition of two other functions. So these type of examples are very important in calculus. If you're going to be taking Calc 1, 2, and 3, you will be get very familiar with recognizing composition of functions. So it's very important to make your transition into the higher level maths easier to learn this skill now. In this course, we're really not going to use it all that much, but this is more of a skill builder for something down the road, so you don't have to learn two things at once. So the idea here is we're going to have this function h of x, and we want to find two functions that when we compose them give us this. So let's write this function and see if we can come up with something. So we have h of x is 3 times the square root of x squared minus 3 minus 9. And the idea here is you want to find an expression in x in here that you can replace with a single variable x. And what I want to pick first here is this expression under the square root, the x squared minus 3. And so I want to create a new function that's almost identical to h of x, but it's going to replace that expression with x squared, or the x squared minus 3 with an x. So we need to make the x squared minus 3 go somewhere. Well, that's going to go to the inner function here, g of x. So we're going to let g of x be x squared minus 3. And then our outer function is going to be this new function we're creating that replaces the square root, or replaces the x squared minus 3 with just an x. And my claim here is that if you compose in this order, you should get h of x. So let's verify that. So f circle g of x is f g x, so that's the order. Remember, you write everything in order. Parentheses go around the x, parentheses go between the f and the g, and this closing pair goes at the very end. And then we're going to take this expression for g of x, and we're going to plug it in here. So we are going to get that this equals f evaluated at x squared minus 3. So remember what our example says to do to evaluate f at an expression. You write down f. So here's f. So we're going to write down f. But everywhere we see the variable x, we're going to replace it with a parenthesis. So we'll have 3 times the square root of a parenthesis minus 9. And then whatever inside the parentheses here goes inside the parentheses here. So that will be x squared minus 3. So let me write that more cleanly here without all the arrows. And notice that this is just the function h of x. So the answer is correct. So we have found two functions whose composition makes h of x. One of the good/bad things about this, though, is it is not unique. So let's look at let's look at the sample again from another point of view. So again, I'm reminding you that we're looking for f circle g of x. And we want it to equal h of x equals 3 times the square root of x squared minus 3, all minus 9. So let's move this over a little more. You can write the 9 more cleanly. And so this example, that was the first solution. So a second solution here, and this has a special name, is known as the trivial solution. And unfortunately, we never want the trivial solution, but I should show you what it is so you can avoid it. So we're going to take the x here and replace it with x. So we're going to let g of x be x, and we're going to let f of x be 3 times the square root of x squared minus 3. Oh, sorry, I wrote this backwards. We're going to let, no, I wrote that right, sorry. Minus 9. And so let's check and see if this is actually correct. So if we look at f circle g of x, well, this is going to be f evaluated at g of x. And g of x is just x, so this is going to be just the function f of x, which we have defined here. So this is just 3 square root of x cubed, or x squared minus 3, minus 9. And so this is just exactly what h of x is. So notice that this solution didn't really change anything. And the whole idea about composition is you want to choose an expression so h gets transformed into something different for the outer function. So notice that my choice of x here, while it worked, didn't change h of x, or didn't change the outer function into a different function. Whereas over here, my choice x squared minus 3 changed the function I was given, 3 to the square root of x squared minus 3 minus 9, into the function f, which was slightly different. So that's the goal of composition. Let me show you one more example. Let's see, we have f circle g of x again, and again we're looking at the same function. So this time I'm going to let g of x be the square root of x squared minus 3, and we'll let f of x then, so we're going to replace the entire square root now with just x. And again, if you check this will actually work, but let's make sure I wrote everything correctly. So let me see, we have f circle g of x is equal to f evaluated at g of x. So this will give me f evaluated at x squared minus 3. This will give me 3, and then we're going to put a parenthesis here for x minus 9, and we just fill in the square root there. But that's just basically h of x, so it does work. So notice that there are multiple ways to go at this. I don't think we could find too many more expressions. I could think of one off the top of my head, but notice there are multiple ways to find a composition of functions. And there are processes in calculus that take advantage of this. So I'm just going to do one more example because I did all these with f circle g, so I want to do at least one example with g circle f so you see that. And then I'll leave the rest to calculus. So one more example. We're way down here. So now I want to find two functions, so when you compose it as g circle f, you get this function right here. So there's a couple ways to go at this. One bad way to do this is to let So we need to replace something with x. So one thing you might want to say is maybe you want to replace the entire expression. Now notice that your inner function is f of x. So your f of x becomes your x plus 1 all squared. But then notice that your g of x, your g of x, which is your outer function, should be your transformed version of h of x. So g of x, so we took everything out, so we just replace it with x, and notice that we get the trivial solution, which we said we never want. So this is not a good choice. So what is the good choice? Well, let's just maybe replace x plus 1 instead. So we're going to let f of x be x plus 1, since f in this case is the inner function. And then the outer function g of x is going to be h of x with x plus 1 replaced with x. So this will just be x squared. And then let's check and make sure this composition works. So g circle f of x is g evaluated at the expression for f of x. So we're going to take x plus 1 and put it in for f of x. Then we evaluate g at x plus 1, so we have an x, so we put a parentheses in for that. We put the square in on the outside, and then we put an x plus 1 in the parentheses. And this is exactly our h of x. So this works. So I hope you learned something and this helps you compose your functions, because I know this is a difficult subject for a lot of students. Up next, we're going to talk about another topic that students have a little bit of difficulty with, is one-to-one functions. And I'll see you then.